Okay, up in the Arctic Circle again, this time to talk about the differentiation, the derivatives of composite functions. So we can just go straight in. I'll share my screen. I'm going to the notebook, and here we go. So let's just clear one or two things down. Okay, so composite functions. Well, what are we talking about? Well, we've come across this in GCSE. We've seen things like G of f of x. It's normally written G f of x. I kind of like to keep the brackets in there because it's showing me exactly what's going on. This concept basically is that you know, we've got two operations going on x. You know, we're going to feed x into this thing called f, which is you know, defines its shape. You know, it could be we could square it. We could have square it and add 3x squared plus 3, or we could take the cosine of it, or whatever. And then we feed the output of that, call it f there. And then we're going to feed that into some other operation, which is g. And the output that we get there is a sort of a two-step operation. We might actually merge these things together. I mean, you've seen the GCSE where you know, if g equals x squared plus 1 and f equals 3x plus 2, then what we're going to end up with is we're going to take our composite function there and we're going to actually stick it in there for that x. So gf would actually end up being 3x plus 2 squared plus 1. And we'd probably expand that and simplify it and present it as one single composite function. Well, you can't always do that. I mean, you know, if we have more complex things using exponentiation and trigonometrical ratios and so on, then it's not always necessary or desirable to do that. So we may well end up with a composite function that looks something like you know, e to the power of sine x. So sine x would sine would be your f, and e would be your g. So that's kind of how that works. So let's just have a think about what we would have to do if we wanted to differentiate this, if we wanted to find its derivative. Okay, so let's look at one example of this. Let's think of the example where, for instance, g. We'll do it the other way around. I think I'll have g equals sine of x, and f is equal to x squared. So if we're to do this substitution that I'm talking about and try and, you know, bang it all together, then we'd end up with g of f would be equal to sine of x squared. So fairly straightforward composite function. Okay, so how do we actually differentiate this? So what we're trying to find here, if we're differentiating this, what we're actually trying to find out is how does g vary with x? We're actually trying to find the g dx, the rate of change of g with respect to x. Now this is where we can we can bring in the chain rule. And I'm not proposed to prove this here, but this is something we can use. Okay, so it's a bit like cancellation, the DFs cancel out. So let's have a look at this. So G is sine. So let me write this a little bit differently. So what we've got here is we've got G equals the sine of F, and F equals x squared. That's really a better way of looking at it. So first of all, if we want to find the dGdF, well, the derivative of that then is going to give us cos F. And if we want the derivative of F with respect to x, then that's going to give us 2x. So going down here then, dGdF, we've seen from up here, is cosine of F times dF dx, which is 2x. Okay, so now what is F? Well, F is x squared, isn't it? So we can actually put that in there as cosine of x squared times 2x. And we'd probably rewrite this as 2x cos x squared. So that's a kind of more usual way we would see it in maths. So just to recap, you know, if we find the right lettering, I think it all becomes a little bit more obvious, doesn't it? So we've got G equals sine of F, F equals x squared. So there's a little bit of confusion, so kind of coming here from GCSE, where we're actually using the same letter twice effectively. This confuses things. So G equals x squared plus 1, F equals 3x plus 2. We're actually using this same letter x, and it's a bit ambiguous. But if we just go back and use G and F, then it works out a bit more straightforward, I think. So that's one example there. Let me just do another example, shall we? Okay, so what about, let's go back to this original example here, e to the power of sine x. Okay, so here what we've got is our f is sine x, and our g is e to the power of f. Okay, so now, so the g dx, that's what we're trying to find. We're trying to find how this function g varies with x is going to be equal to dg df times df dx. So dg df, we can see that g is equal to the power of f, and e has this property, doesn't it, that it kind of differentiates to itself. So so that's going to be e to the power of f, and then the f dx, well, the f dx is cosine of x. But what is f? F is sine of x, so we've basically got e to the power of sine x times cosine of x. And that is the derivative of that. Okay, so I think by using our letters correctly, then we can see that the finding the derivative of a composite function is really the same as differentiation by substitution, and that is really the same thing as the chain rule that we've got here. So all those concepts are really kind of meld into one. We might, it's also worth kind of maybe doing one more example. So let's have a look at this one. So example, if I can write it correctly. Okay, so let's just do this polynomial. So we've got 6x squared plus 7x all to the power of 4. Now we could actually expand all this, couldn't we? We could do a sort of an expansion of this where we get to some term to the power of 8, the left hand end, and and then decreasing powers, and then we could just apply the power rule and just do the whole thing together. Probably slightly easier actually to use the chain rule. So let's have a look. Well, we've got this thing on the inside, so this is telling me that our f is 6x squared plus 7x, and therefore what is g? G is f to the power of 4. Okay, so we're going for dg dx, aren't we? That's what we ultimately want. This whole thing is g, and that's what we want to find its derivative with respect to x. So we're going to do a big part. We're going to do it in bits. So the g dx equals the g df times df dx. So the g df, well, that's the power rule. That's 4f to the power of 3, and then the f dx is going to be, by the power rule, is going to be 12x plus 7. Again, what is f? F is given here. We can substitute this back in, so that is going to be 4 times 6x plus 7, 6x squared plus 7x, all to the power of 3, times this 12x plus 7. Okay, and again we can expand this if we wish, but what I'm doing here is illustrating the point. Okay, so that's how it works when we've got a composite function of 2. Sometimes we get a little bit more complicated than that. We could get something like e to the power of sine of x squared plus 1. Right. So now what we've actually got, we've got a kind of three level composite function. So we're actually talking about h of g of f of x. Okay, so we can extend the chain rule now. What we need to do first of all, I think, is identify what we're talking about. So if the sort of the inside of all this, these are nested functions, aren't they? So we've got f is going to be x squared plus 1. Our g is going to be the sine of f, and our h is going to be e to the power of g. So what we've got is we've got dh dx is what we're looking for. We can see that in terms of dh dg times dg df times df dx. And if we work all that through, dh dg is it's e to the power of g. Well, e to the power of g differentiates to e to the power of g, so that's going to be e to the power of g times dg df. Well, dg df, g is sine f, so dg df is going to be cosine of f times df dx. Well, the power rule gives us df dx is 2x. Okay, so that's what we've got, but then we have to put our substitutions back in. So e to the power of g is going to be e to the power of sine f times cosine of f times 2x. But then obviously we need to do our f substitution. So we've got e to the power of sine of x squared plus 1 times cosine of f. Well, f is x squared plus 1, so we've got cosine of x squared plus 1 times 2x. So this is the derivative of that. Okay, so another illustration, I think, is if you can actually spot the functions and give them the letters. I think I would, tend to use G and F. That relates it back to composite functions that we learnt at GCSE. You might find that easy to do. Then it kind of it simplifies the exercise. So yeah, derivatives of composite functions, to spot the structure of the composite function, and then just apply your chain rule here, and then apply your substitutions back at the end, and it should all come good. Okay, so I hope that's been helpful. If you like this video, then please give it a like or an upvote, and I'll see you in the next video.